All right, welcome to week 9. So we are joined by a guest today, without whom I would absolutely not be where I am here today. All of you, as you know, have FAS accounts, and that stands, of course, for the Faculty of Arts and Sciences, which comprises Harvard College, the Graduate School of Arts and Sciences, the Summer School, the Extension School, the libraries, the athletic facilities, all of that, really Harvard in the truest sense. And we're quite pleased today to have the man who's in charge now of all of that. So Mike Smith is the Dean of the Faculty of Arts and Sciences, and more personally, he was also my advisor in graduate school for 5 years. And perhaps most importantly of all, he was also the instructor for this course for a good number of years. And it is our great pleasure to have him join us here today, Mike Smith.
Thank you, David. Thank you for that. You might want to wait until after the lecture to decide. So what I wanted to come back and talk to you today about was one of my favorite topics, which is writing secure code. It's interesting because it gives us an opportunity to try and break things. Many of you have probably read in the newspaper about things like buffer overruns, or heard in this class the way people try to take over machines, use those machines as zombies to send out the thousands of pieces of spam email that you get every day, and wondered how people go about doing those sorts of things. That's our goal today. Our goal is to look at it and say, what does it mean to write secure code? And in particular, what are these things called buffer overruns? How is it that some person who isn't me sitting at my computer right here can actually take over a person's machine to start doing something which the machine wasn't originally expected to do? Along the way, we'll also talk about dangerous functions. What we're talking about here is how can we generalize what we're seeing with buffer overruns to understand, again, what does it really mean if I have to build a piece of software, and that software is not only supposed to run fast and have certain capabilities, certain functions that allow us to perform whatever action we want, but keep performing those actions in the face of adversaries that are determined to make it do something else. That's what we're going to try and do here, and talk about how you can write functions that are better at doing that than functions which are easier to take over. So I thought I might start by just putting up a couple of these articles are getting a bit dated, but an article that motivates why it is that we're specifically looking at what a hacker might do, hacker in the bad sense of the term here. This article is saying that really in order to fight adversaries in the world today, we have to be able to think like adversaries. What is it that someone who's trying to take over my machine, for example, to send spam, really going to do? So again, I'm going to be teaching you how to do this today, or at least explaining how to do it. Hopefully you all realize you shouldn't go out and try this at home. Try it on your own machines, but please don't use it for nefarious purposes as we go through today. There was also some interesting, for those of you that are interested in virtual games or these virtual worlds that exist out there, they're not immune to these kinds of activities too. This was last year, I think. They were talking about worms hitting Second Life, and it got so bad that actually they shut down Second Life for a while because people were doing things that disrupted the world so much. And this obviously costs lots and lots of money to Second Life. So let's get specific here for a moment. What I want to do is look at string processing as a way of doing buffer overruns today. In this class, you've been using a CS50 library called CS50.h, and in that are copies of routines that allow us to do simple things with our strings. So you've been using this function called getString out of that library, which was a reimplementation of an original Roberts library function. You also did some work with copyString on a test, I'm told, recently. Does anyone remember what was said about getString and why getString is possibly not the best function we might want to write to actually get a string? Yes? There's a memory leak. Exactly. When you call getString, it silently gathers some memory behind the scenes, and if you're not paying attention, you're not using the operand, the getString function correctly, you can end up running out of memory in your system without realizing it. We've hidden behind that interface some functionality that's not clear from the simple interface. CopyString had a similar kind of problem. The right-hand side of this slide, do I have any pointing devices? No? OK. On the right-hand side of this slide are the ANSI libraries. These are the ones that see in the governing bodies that put forth what you should have on every machine where you try and run a C program, say, here's some library functions you might want to put into your programs. The issue here is, should you be able to use all of these functions, or are they dangerous in the same way that getString was actually dangerous? Well, there are a couple. String cat and string copy are functions that you may be told in the beginning, go ahead and use, but as you get out in the real world, you should probably never use these functions. And you might go, well, why is it in a standardized library that exists on every machine? And the simplest answer to that question is, these are low-level routines. These are basic functions put together in the first place for performance reasons. I can do a copy of a string from one location to another location doing basically nothing but the copy, and that's what I'll get out of string copy. But you get nothing but the copy. You don't get any checking, you don't get any sanity checks on the world. And we're going to take advantage of the fact that you get no sanity checks on the world to actually destroy the function of a program today. There's actually a whole bunch of extra standard I/O kinds of functions, that input-output functions, that exist in these libraries. And the same thing is true here. There's a number of these functions which are just incredibly dangerous, and you should actually never use them in production code. In particular, getString and scanf, which we'll talk a little bit about later in today's lecture, are again functions that don't ever use. They are so dangerous that it makes no sense to use them. If you're smart about it, you can absolutely use them, but there's a better set of functions in the world, as we'll talk about later. Even printf and fprintf, they can be used in ways that are less than ideal. Now, we use them all the time, and there's not much other ways of printing out a string other than printf, but we'll talk to you about some ways that you can actually write memory using printf, which is not exactly what you would think you could do with a printf function. So I've been saying that it's very hard to write secure code using these functions that I've crossed out, or these functions that I've boxed here. Your first question should be, what does that really mean? What does it really mean to write secure code? So we'll have some fun here for a moment. What is secure code? In my time, I've listened to a number of people try to give answers to this question. One of the answers that comes out is, well, secure code is code without comments. Yes, it would probably be very hard to understand what your code is doing if you have no comments in it, but that's not what we mean by secure code. It's one way to obfuscate your code, make it hard to understand what it's trying to do, but it really does nothing to actually keep an adversary out of your code base. The adversary can, just like your TFs in this class, actually figure out what the code is trying to do. So that's not a good definition. Others say, look, I have secure code. This is oftentimes in marketing literature that you'll get from software companies, because I have cryptography in my code. Does cryptography, the use of cryptography in my code, actually make it secure code? Unfortunately, the answer again is no here. Just because you have code to implement security features doesn't mean you've actually implemented those security features in any meaningful way. Oftentimes when people break systems that have cryptography in them, they're not breaking the cryptography. They're breaking the system around it. How did you get the code or the text into the ciphertext or back out of the ciphertext? Did you just leave the key that you used lying around in memory, for example? It's much more simple to pull that key out of memory as the program's using it than it is to actually try and break the cryptographic text and understand what it was doing. So that's not sufficient. What about code that is hard to use? Is that secure code? Actually, people have given me this answer. It's hard to use, therefore it must be secure. Again, the problem here is that unfortunately most software that's sold today that is talked about as secure code is actually hard to use. That doesn't mean you should be doing that, right? Just because your code is hard to use doesn't get us any real security. It's just an unfortunate side effect of people trying to make their code secure, that they end up making it very difficult for us to use. Not a good answer. Here's one that might be a little bit more difficult to answer. What about code written in Java or C# or some other favorite new language that exists out in the world? If you've been paying attention to the marketing that comes out about C# and Java, one of the things that they talk about is the fact that you can write secure code with Java and C#. So again, the question really is this sufficient? The answer here again is these help. These new languages avert, in particular, the kind of problem I'll demonstrate today. It's much more difficult to write in a Java program an application that will have a buffer overflow and therefore be able to have the kinds of attacks we talked about today, because the string is a base data type in those languages. Therefore, it's much harder to do the kinds of things we're doing today. But you can still end up, as I'll talk about a little bit later, with issues that cause you to have insecure code in this world too. So it's a good starting point, but not sufficient. What we really mean when we talk about secure code is the fact that we're thinking like an adversary and really trying to make our code robust, trying to make it withstand the kinds of attacks that a malicious user might try and push on the system. So far in this world, in this class, you've probably been thinking about what kinds of things might happen, but not from the point of view of what kinds of things might a person actually push into this system to make it do something specifically wrong. It's a subtle difference there from, can I put in inputs into this world that cause a problem versus will somebody sit around and think for a long time to come up with a specific input which actually works on a corner case in my program and actually has a bad thing happen. That's what we're trying to get away from in this set of lectures here today. So the reality in the world is that if you create an application today and you put it on the internet, your code will be attacked. There are an amazing number of people out there with lots and lots of spare time on their hands. And they will look at ways of trying to, if your system is at all interesting, try to find a way of breaking your system. So what people talk about when they talk about building secure code is designing with security in mind from the beginning. From the first thing as you're talking about what kinds of functionality I need my particular application to have, security, if you're running on the internet, needs to be one of them. It can't be brought in afterwards, right? Just like any other big design project, having a requirement happen at the end is never a good thing. It's much more expensive than in the beginning. The last bullet up here is just to remind you, if it hasn't been clear from the assignments in this class, your software almost always has bugs in it. Right? No one writes perfect software unless it's a really, really small program. And these bugs are what typically lead to security failures. All right? I did something wrong in my program. I didn't realize it. Someone else comes along, realizes that I did that, and then tries to find a way of taking advantage of that bug for his or her own purposes. So I actually had a VP of engineering at a company I was working at once who had two rules in the world. Right? First rule was this one that we're talking about here. Rule 1, software contains bugs. That was rule 1 in her world. Rule 2 was management can't change rule 1. So no matter how much management wants to come along and say, this is a perfect program, we've got to ship it now, and they'll say that to you, you have to realize that it will be shipped with bugs in it, and thinking about how those bugs can lead to security failures is extremely important. So let's get into the specifics of how we're going to have the system be attacked today. So as I mentioned, we're going to look at one specific kind of attack today, and that attack is called buffer overrun attacks. The adversary's goal in a buffer overrun attack is very simple. They want to have the program control end up someplace it shouldn't be. They want to be running a piece of code that you did not expect to be running in this program at this time. All right? Buffer overrun itself is like it talks about. I'm going to simply write some data into memory in a buffer that's smaller than I need. I'll write data into this buffer, and then I'll keep writing beyond the end of the buffer and start writing other pieces of memory. This has to end up with this goal, that by writing extra pieces of memory beyond the end of my buffer, I can actually change the program's control flow and end up someplace else. So the cause of this is fairly simple. We're just poor coding practices. As we were talking about a little bit earlier, I can use one of these dangerous functions which don't check, for example, sizes of buffers in ways that I should have checked before I used the function. So this is just a poor coding practice. It ends up oftentimes with buffer overrun attacks as talked about as a language feature that's missing in the language, because newer languages like C# and Java make strings a native data type and manage this behind the scenes for you. So you can't take and write a number of characters into a string that is larger than the amount of space that you've allocated for that string. The language will do the checking basically in the compiler by generating code for you. C was supposed to be close to assembly languages you probably talked about earlier in this class, It says the programmer's responsibility is to do all this checking. I'm just going to do whatever minimal amount of work I need to do so it can be done as fast as possible. So you'll see this in C and C++. By the way, you should stop me if there's questions. I don't need to just babble the whole time. Now, buffer overrun attacks, well, this is really dated now. Back around 2000 were huge. Almost 50% of the types of attacks that were being seen in the world were all due to buffer overruns. You would think now, 8 years later, that this wouldn't be true. Unfortunately, there's still a huge component of the kinds of attacks if you go out and look. And many of these advisory systems don't even track it anymore because there's just so many of them. It's not worth their effort to track how many come up. So let's look in details about how to make this work. So here's a simple piece of code. I'm told that you have seen this recently. What does this do? Anybody want to help out? Sorry, yes, there you are. Go ahead, say it. Exactly. This is very simple. It's just like the built-in echo command. It just takes whatever strings you put after the file name, after the program name, and echoes it back to the terminal for you. Right? A simple loop that says for all of the input arguments that you gave me, simply print out each one of those input arguments. All right? I'm going to try and make this into, by the way, as a safe program, wasn't doing very much, into an unsafe program by using one of our functions that I told you we really shouldn't use. So here's, in main, basically the same program that's going to echo out our program arguments. But instead of calling printf directly in the main routine, I'm going to call a helping routine. And I'm going to do a little functional decomposition here that's going to say, for all the work that I want to do, the only thing I'm supposed to be doing this loop is echoing out each argument. So I'll create myself a little function called echoarg, which is going to take in the string that I'm supposed to echo. And then the code up top just says, take that string and create myself a little local buffer into which I can put that string, make a copy of the argument into that local buffer, and then call printf on that local buffer. So what's the problem with this code? First of all, will this code work? Safe question. I don't know if David does this, but I love, this is computer science, binary questions, yes, no. 50% of the time you'll be right. It's a good thing. Yes, these compiles, and it will do something. What's the problem? Exactly. So I have a local buffer, right? If I declare a variable inside, do I have a pointer on here? I do, right? Yeah. If I declare a variable inside of my function, echoarg, it's a local variable. Where do local variables get stuck? On the stack, right? This buffer has a certain size, since it's a compile time variable. Here's my cursor. And I have defined it to be no bigger than max buff size. Max buff size isn't on this slide, but pretend for a second it's 4 characters. So I have a buffer of 4 characters here. It says copy whatever string you got from the argument line into that buffer. If I'm trying to copy a string bigger than 4 characters, does string copy keep copying? It does. Right? String copy, all it cares about is take everything in the first string, s, and copy it into the second string, buff. When is it going to stop? What's the end of s? Null character, right? Oh, you did a good job, David. Right? A string in C is defined to be anything you find until you hit a 0 character, the null character. So string copy says take the first character in S, move it into the first location in buff, check to see if it's the 0 character. If it isn't, keep going, right, until you hit a 0 character in string. Cares not a whit for max buff size. All right? So let's play for a second. So I'm going to switch back and forth here. I have a Science Center-like machine on my machine. So here was echo this. All I did was rename this program to call it ECO. It basically has the same code that you saw earlier. So I can create myself a shell here if I do this right. Oh, let's do this. Hold on. There we go. So I'm running an Emacs, if anybody's curious. So I think I already compiled this. Let me see. Oops, wrong file. There it is. So ECO-L foo. So I said echo ls-l foo, and it happily echoed ls-l foo. No problems at all. Why no problems at all? They're all smaller than max buffer size, right? I told you max buffer size was 4 characters. ls is 2 characters plus a null. -l is 2 characters plus a null. Foo is 3 characters plus a null. It all fits. What if I do... Oop, thank you. Is this good? Probably most of you are, no, I hate this. I dumped core someplace, right? Why did I dump core? I went and wrote memory that doesn't belong to me. In particular, what I had a problem here was make was 5-character string, if I put the right number of fingers up, 5-character string, right? So the terminating null from the string copy copied over some other data in my world. I was able to print out make because that was before I tried to use any of that other space again. But as soon as I was done printing out make, that extra null went off to some place it really shouldn't have and caused the rest of my program not to run correctly. Okay? So, can we be even nastier here is the question. Having your program die is a bad thing. Having somebody else be able to feed you inputs that causes your program to die, a bad thing. That's one way of attacking a system. That's basically called denial of service. I'm running in Second Life. Somebody in the next room over is doing things that cause Second Life to keep crashing. I get annoyed. I go someplace else. Second Life doesn't make any money. Right? That's one way of doing this. But perhaps I want to be a little trickier, and I want the person to continue to use Second Life, but I want to get all of their, I've never done Second Life in my life, but you know, their Second Life money. All right? Can I have that happen without them knowing it? So I'm going to change this routine a little bit by adding one more function. Okay, there's just comments at the top here. Let me see if I can make this whole thing fit. Almost. You don't need to see the pound includes. Right there. Okay? Here's that same program again, except I've added one more function in the world called gotcha. Will this program ever run gotcha? 50-50 answer. How many people say yes? How many people say no? Raise your hand. I know, it's 10 o'clock in the morning. It's a lot of work. Come on, participate here. Hopefully most of you are saying, no, there's no call, right? Everything that David's taught me says, in order to get to a routine, I need to see that routine's name someplace in my code. Gotcha is not called anywhere in main. You haven't done indirect function pointers yet, right? Eventually you'll learn how to do through a function pointer, which is really cool. But for now, you need to see the name. And it's not called in echo arg. Echo arg is called from main. Main is called when I start running the program. I should never get to gotcha. I should never print out the word lowercase gotcha, right? Okay. Well, let me do this. I'm going to cheat for a moment, and then I'll tell you why. That's all I need. Okay, so I got some garbage coming out, but then it printed gotcha. So the question here is, what did I really do with hack.pl? Hack.pl is just a little Perl program. And it's a little crazy to read Perl. It's in many people's opinion, a write-once language. But what we're trying to do here is create a variable called arg and put some text into it. And the text is 1, 2, 3, 4 concatenated with a bunch of hex characters concatenated with a bunch more hex characters. All right? That string is then concatenated with the file name, with the program name, which is arg0 here, which is the first thing I passed the Perl string. And then I asked the system to execute this just as if I had executed ./eco space some argument string. Why am I doing this? I'm doing this because I need to put some unprintable characters into memory. Right? ASCII code only takes a small number of the 256 different characters different values that you can stick into memory. And in order for me to change what I need to change in order to get someplace, I need to put an unprintable character in. You could claim this is a cheat, but hey, this is programming. I can do whatever I want. Why is this really doing what I'm saying you're doing? By the way, you see no gotcha here, right? But you may claim that, Mike, you're screwing around with this. So let me change this to be, by the way, the pound sign is just a comment character. Now I'm just going to pass in the string ls-l-foo, just so you believe I'm not doing anything really tricky. So it just prints out ls-l-foo. So I really am just passing it as string, and then having echo arg, or ECO in this case, just execute with that string being passed into it. It's just a string that you wouldn't be able to type from a normal keyboard. OK? So let's, first of all, before I forget, put this back. Let me get out of this for a minute. So my goal now is to convince you of how this actually works. So this is what we had. All right? What's key in order to do what I have just demonstrated you can do? Well, there's a couple of key elements in this. First, you need a fixed size buffer. For what we're trying to do, a fixed size buffer is important to us because we need to be able to run beyond the end of that buffer. So we got that, in this case, through the use of this buff. Right? There's our fixed size buffer. I also need it, as this next slide talks about, to be declared on the stack. And in a moment, this will be clear why we need it declared on the stack, because that's where we're going to go write something that allows us to change where the program actually ends up executing. All right? So we'll talk more in detail about that in a moment. Second thing I need is an unsafe function to actually write the contents of that buffer. What does that mean? That simply means I need a function that allows me to write beyond the end of that buffer. A safe function would not allow me to write beyond the end of that buffer. I could not do anything to make this program break. Third thing I need is to make sure that nobody actually checks the input that I sent to this buffer. Why is that? Exactly. The whole thing, this crazy thing I did with Perl as a front end to sending input into my program is so I could send in something that didn't look anything like a character. If one of the simple checks I did on a string that was being passed to this echo argument function is check to make sure that the characters being passed are printable characters, it would be much harder to break this system. All right? Not impossible, but a lot harder. Third thing, in order for us to get into a function that otherwise is never called, I need to be able to change a piece of memory that is used as a location to start executing in a function. So we're going to go about changing the return address for a function on the stack to match the beginning address of the function you should have never gotten to. That's what happens. So let me start drawing some pictures on the board so this becomes hopefully a bit more clear. So you've talked about stacks and memory in this class, right? So if this is a picture of memory, so we'll make this our memory. And I'm going to put low memory at the top and high memory at the bottom. This means that if you were paying attention earlier in class, stacks grow up, well, up on the board, or down in memory, from high memory to low memory. So what's the first thing when the program starts running? What happens to the stack? What do I get in my stack? Main, right? I create a stack frame that is main. As long as I'm executing in main, I'm perfectly happy. Inside of main's little stack frame here goes things like local variables and so forth. At the time that I get to, let me put this back, the line that says echo arg inside of main, what happens? Go ahead and speak up, someone. Right, we stuck a new stack frame on here called, what did I call it? Echo arg? Right? A new frame comes on here. And inside this frame goes things like buff. Right? Once we've executed echo arg, what happens? It goes away, right? This whole thing gets erased. The real question is, how does, when this thing gets erased, I know where to go back in main? That works by, before main actually goes off and starts executing in echo arg, it squirrels away a little piece of information in the stack frame, which is its return address. I'll write this out a little bit farther. It says, I was executing along, and I now need to go off and execute in echo arg. When echo arg's all done, I'd like to start again at this point in my main program. So you can think of it as a line number. This is just a line number that we've squirreled away so that when echo arg is all done and it hits its return statement, it says, OK, where am I supposed to return to? I'm supposed to return to this point. Okay? If I put something in buff, which way do characters go in buff? Toward low memory or toward high memory? If I put something in the 0th location, then the 1st location, then the 2nd location, is the 2nd location toward high memory or toward low memory? Toward high memory, right? So if I start writing buff, I can eventually write the return address if nobody checks to make sure that I haven't stayed within the bounds of buff. And that's all we're doing here. We're setting it up so that I write something into buff, and I write long enough that I can actually overwrite this return address. Make sense? Question? OK, let's look and see if that really happens. I'm going to look and see by playing a little fast and loose with the printf statement. OK? We're going to take a look inside of our program and see what happens as the program's executing along. In order to do this, I want to add some extra code to my program that allows me to see, for example, what's sitting on the stack frame. One way I could do this is start the debugger up and execute in single step along, and then look at the stack frame in the debugger. The problem with the debugger is it doesn't actually print out very nice things to tell me, oh, you're looking at this point, and here's what the characters are that you're looking at, to give me some extra strings. I'd like to have printf format my output correctly so that it prints what's on the stack at different points in my program. Most of you will probably go, how do you get printf to print what's on the stack when I don't have a way of specifying in my program what a stack location is? Right? I always have to give it some string or some integer variable to which it creates a format code and then prints out things. I claim that this printf statement right here prints the stack for me. OK? Why? Well, first of all, the first thing you should note is that I played a little game, and I don't know if you guys have learned this yet, but one thing you can do with printf is just have a bunch of strings all appear next to each other, and the compiler's smart enough to concatenate them all. So you'll notice here that it's printf, open parenthesis, a string that says contents of the stack before a string copy, end string. Next line, with no comma, no nothing, just starts a new string, gives a format code, and says dash dash garbage, end string, and so on. So the compiler is going to be nice enough to say, look, the program that Mike was typing doesn't have a line long enough to fit this big long string he wants on it. So I'm just going to concatenate all these things into one format string. So this is the format string that comes first in your printf statement. It just happens to be broken into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 or 10 pieces. I can't count. Yes? Yeah, so what's being asked about is the 0x %08x, right? Yeah. OK. So those are the format codes, just like %n and %f and %s. The format code actually is %08x. The 0x in the front is just, most of us who are computer scientists know that if you say 0x, what comes after that is hex digits. So that's just part of my string that I'm printing out. The format code there, 08x, the %x says I want to print something in hexadecimal format. That's instead of a decimal format or something else. And the 08 says I'd like 8 digits to appear, and it should be 0 filled. So if I only have 2 digits of hex to print, I still get 6 zeros and then my 2 digits. Just to make the things look pretty. That's all I'm doing there. What's weird about this, besides everything I just explained? Yeah, I have a whole bunch of format codes. The format codes are supposed to say, go find the next variable along and grab its contents and print it out in hex format. And then find the next variable in this printf statement and print it out. I didn't give you any. So where's it going to print from? So should I get a compile error? The C compiler says, no, this will work just fine. You'll get a warning. It says, this is a little weird. But it knows someplace to go. Yes? Right. It takes them where it should have found them. Right? If I had stuck another variable at the end of my printf statement, it would have just been pushed on the stack before I called printf. And printf would have known when it went to do its work that, oh, by the way, I should find the format string on the stack. And then after the format string, I should find the first variable I'm supposed to print, and then the second variable, and so forth. And how many variables it's supposed to print, printf knows by knowing how many format codes it finds in the format string. It says, oh, you're supposed to print 1, 2, 3, 4, 8 variables, even though I gave it none. So it just goes and prints whatever it finds on the stack, as if it was a hex character. So this is a way of saying, I don't want you to print any variables for me. I actually want you to print whatever I find on the stack right now. So we can do this. If I go back into my virtual machine. So by the way, this is here. So here's the exact same program I was running before. Of course, it's a little too big for my screen here, but let's see what I can do. So here's echo arg. Ignore the comment about the canary. That was me playing around. There's the local buff. Then there's this crazy printf statement that appears just before the string copy, and then the crazy printf statement immediately after the string copy. So all I want to know is, what does the stack look like right before I called string copy? And what does the stack look like immediately after string copy? And then I did all the hard work before we got to class today and said exactly what stack location corresponds to what. That's how the print statement actually got to work. So if I run this, by the way, first of all, I can run this without the hack in it to show you it just runs fine. I should have done one. Hold on. That's too much. We don't need all that. Excuse me while I make the screen pretty for you. OK, so I ran smash with ls. It's the same thing as running echo with ls. So eventually you should see ls. And sure enough, down here on the end of the slide, before we returned and got a new prompt, it printed ls. Along the way, it told me a couple of interesting facts, by the way. I printed out in main what the starting address of main was. Starting address happens to be hex 0804845F. The starting address of gotcha happens to be this next string. Then the two prints that we saw right before and after string copy. And then finally the ls. The reason I bring this up is, well, what does this make sense? Well, let's look at the data here. So the last thing here on the stack frame that I was doing for you, which basically exists down here in main, is the base address of the starting argument. The address of the string passed to echo arg. That'll be here, because it needs to be pulled off. And then the return address to get back to main. And then we'll get some registers stored in this world so that we can return back. You don't have to worry about that for right now. And then the actual contents of buff. That's what this says, moving up the screen. Notice that buff before, this buff here, this is the actual contents of buff. It's a bunch of junk right now, as you've been told in this class. If you don't initialize your variable, you get junk. After string copy, you get this. Who here can read ASCII? What should this buffer contain? ls. Exactly. If you read, because this is an x86 machine, from right to left, you get6C7300. And if you go look up in an ASCII table, you'll see 63 is the hex value for L. 7, I don't know it either off the top of my head. 73 is the ASCII value for S, and 00 is the end of the string. The other nice thing is that the return address down here is 080484C2, did not change from before and after. And if you go back and you look at main's starting address, it's someplace in main. So I'll end up back in main. What happens if we run hack smash? Okay, does basically the same thing, but at this time it printed out gotcha at the end with the other junk. Remember the beginnings, or maybe not remember, but the beginnings of my junk string had 1, 2, 3, 4, and then a bunch of hex characters. So the 1, 2, 3, 4 actually ends up in the final contents of buff, reading again from right to left, 31, 32, 33, 34. Hex numbers are, numbers, ASCII numbers are easy to read. It's 3 and then the number. So that's 1, 2, 3, 4. We didn't end the string there. We kept writing. We happened to write back in a similar place for EBP to be restored to. But the next line, the return address for the call to echo arg, has now changed. It's now 080483FC, which if you look at the top of the screen, is the same as the base address of gotcha. So when I return from echo arg, I don't return to main. I return to this other function. And if I'm careful about the EBP contents, EBP is a base pointer to another set of memory that better be good, this program can keep running. It can't run for very far without causing problems, because I wasn't all that careful. Notice I have an exit at the end of gotcha, because the stack is completely screwed up now. I'm never going to get back to main correctly. So I just exit out at some point. Normally, this is not a problem because you want the program to keep running, doing other things. Question, yes?
So how do you make sure that with the buffer, the amount of characters you write gets you to the return address? And how do you know the memory address of gotcha?
So the questions were, how do I know the memory address of gotcha, and how do I know I wrote the right number of characters to actually overwrite a return address? This is where people who have too much time on their hands, right? How did I do this? Well, I did it with a debugger, so you could do that. If I don't actually have the code because it's running on somebody else's machine, it's a server, and I'm just sending it, what do? You just keep sending it junk until something works. And you can automate it, right? And I don't have to send it to one of my own made-up functions. I can send it to a function that exists in the C library. Typically what happens here is I know there's a C library loaded someplace. Most of these programs load the C library in the same place every time. And therefore, I just keep sending it an address until I end up in that routine. And then I slowly build my way up. It's just like, digging in the past. I learn little bits and pieces as I go forward. But that's how it typically works. Yes? Yeah, so the follow-on question is this: how do you stop this kind of an attack? You randomize your memory locations, you do other sorts of things. Not the best way of doing it, but you can get some things done. So I'm running out of time. Let me just fly through these other couple of slides because they're pretty straightforward. I always have too much fun in breaking the machine. So this is a couple of ways to prevent these. Validate your inputs. Define string copy, so in case you type it mistakenly, your program doesn't compile, so forth. I might mention that I've told you one way of breaking the system. Unfortunately, it's not a rigorous way of protecting your system. People have a lot of rhetoric in the world that are all fairly straightforward and sensible things, but hard to actually implement and check for in terms of programs. I told you about buffer overruns. The same thing can happen for overruns in the heap. I don't have to have my string on the stack to make this happen. I can actually stick it in memory with a malloc call. The next couple of slides tell you problems that they exist with some of these functions I mentioned earlier. Let me just focus on printf for 1 second. I told you that printf could be used dangerously. Why? Because you can write a format string that says, down here on the bottom part of the slide, %s, %n. And %n means actually write into a variable the size of the string that you wrote just previously. So in num here, you would get the size of the hello string. How can this be a problem? Well, if you scoot back up the slide for a second, you can actually write printf with just a string, right? A variable that's a string, no format string. I don't have to write printf open double quote, %s, close double quote, comma, a string variable like hello. I can just pass hello, because hello as a string becomes the format string by default. This is where you get into trouble by allowing the user to define your format string, and then the user comes along and defines a format string that writes memory. And then you've just given your program over to the bad guys. OK? So don't ever do that. Always define your format string. And then the last couple of things are just suggested readings. If you want to know more about secure coding practices, go for it. Last questions? All right, then otherwise, happy Thanksgiving from all the CS50 people.